Welcome, ladies and gentlemen. My name is Phillip Richter-Pechanski from the Discharge lab in the Heidelberg University Hospital at the Cardiology department. Today, I want to show you our results about automatic extraction of 12 cardiovascular concepts from German discharge letters using pre-trained language models. Let me give you a quick overview about this talk. After a short introduction, I will define the objective of our experiments. Afterwards, we will have a closer look at the data we've been using. Then I will introduce you to the deep learning methods we've applied. After looking at the results and discussing some main outcomes, I will sum up the talk and give some information about future work. While structured reporting is an emerging field in the clinical domain, a vast amount of clinical data is still stored in unstructured form. To make these data available for research and clinical routine, automatic clinical information extraction methods need to be applied. Recent developments in natural language processing (NLP) showed promising results using powerful deep learning methods on limited training data. Let us define the objective of this task. In the upper left corner, you can see a snippet from a German discharge letter. It is created in clinical routine using a semi-structured MS Word document. This is a practical example to understand what we want to achieve. Most information, anamnesis, and risk factor sections are stored in natural language. To use the clinical information relevant for cardiologists in state-of-the-art data-driven pipelines, we need to extract structured information from these documents. In the table, you can see extracted sequences of words labeled with cardiovascular concepts, like angina pectoris, dyspnea, etc. It becomes obvious that often this information is just described implicitly in the documents and not explicitly to store them in a structured form. For example, if we have a look at the angina pectoris, the extracted text here is describing it with the words belastungsabhängiges thorakales Druck- und Engegefühl. So, as time is crucial in clinical domain and annotations are needed for state-of-the-art supervised deep learning methods, recent developments in NLP using pre-trained language models show promising results on limited training data. Thus, the goal of this study was to evaluate pre-trained language models on token classification tasks to automatically recognize and classify 12 cardiovascular concepts from German discharge letters from the cardiology domain. Let us have a closer look at the data we've been using. Here you can see a dummy discharge letter from our department representing the semi-structure of these MS Word documents. So, for example, they contain sections like diagnosis or anamnesis. We extracted a set of 203 German discharge letters from our main corpus, covering a time period from 2004 to 2016. Cardiologists manually annotated the anamnesis and risk factor sections with a set of 12 cardiovascular concepts. In total, 4,700 words of approximately 380,000 words contain cardiovascular concepts. Pre-trained language models established a totally new NLP deep learning workflow. The terms pre-training and fine-tuning are crucial here. Looking at pre-training, we see a semi-supervised task. The goal is to train a language model on large amounts of natural language data, for example, the whole Wikipedia dump or a clinical corpora containing discharge letters. We do not need to manually annotate these data because the objective of training a language model is already satisfied with the input datasets. Simply speaking, the objective of a language model training is, given an input sequence of words, predict the next word. For example, Joe Biden is, and the model shall predict president. Finally, the language model learns numerical representation of words incorporating syntactical, semantical, and contextual information. Looking at the fine-tuning step, we see a supervised task. We take the pre-trained language model and fine-tune it on our manually annotated dataset containing cardiovascular concepts. So we take the language model for encoding the input sequences of words and stack on it a classifier, which, for example, classifies words into these three categories: dyspnea, angina pectoris, and edema. So if we input the sequence es besteht außerdem progrediente Belastungsdyspnoe, the classifier shall recognize the words progrediente Belastungsdyspnoe and classify it with the cardiovascular concept dyspnea. To compare the performance of our BIRD approach, we are using a well-established statistical machine learning method based on a conditional random field. For training and evaluation, we are using four-fold cross-validation. As metrics, we are using token-wise F1 score, the harmonic mean between precision and recall, better known as sensitivity. F1 score is usually used for token classification tasks to manage the high amount of true negatives in the dataset. We've seen that when I showed you our data, the annotations, so just 4,700 token in our dataset from all over 380,000 token contain cardiovascular concepts. Looking at our results for cardiovascular concept extraction, we can observe that the BIRD approach outperforms the baseline over most classes. This is especially true for the classes angina pectoris, dyspnea, edema, and schwindel. Having a closer look at the angina pectoris, dyspnea, and edema classes, we see in the annotations very long sequences in the dataset, making it a huge challenge to automatically predict these labels, which the deep learning BIRD approach manages much better than the baseline. Overall, the BIRD model achieves 86% token-wise micro-average F1 score, which is 8% better than the conditional random field. Using a four-fold cross-validation, we observed as well instabilities in different dataset splits. This might be due to the relatively small dataset size. Still, using approximate randomization at significance testing, we observed a significant performance improvement of the BIRD model over all folds. Let us sum up our study's results. The publicly available BIRD model, pre-trained on Wikipedia and legal data, outperforms the baseline using token-wise micro-average F1 score by 8%. The results show the applicability of BIRD for automatic cardiovascular concept extraction on limited training data. This makes it a promising interim solution to foster development of deep learning-based NLP methods for automatic clinical information extraction tasks in various languages, especially low-resource languages like German, where there is a lack of shared annotated data. To overcome instabilities in the dataset, we plan to increase the dataset size. To improve annotation speed, we will use methods of weak supervision and active learning. These will be applied in a German Research Fund funded project targeting at the creation of a user interface to involve clinical domain experts into a deep learning workflow. Finally, we are planning to publish a clinical corpus containing 500 discharge letters from the cardiology domain for the research community. Thank you very much for your attention. I am looking forward for your questions.